sir. Today's experiment is on experiment number 4, uniform quantization and pulse code modulation or PCM using Python. The main objective of this experiment are to implement a uniform quantizer and PCM encoder from the first principle, understand the relationship between the number of bits, quantization error, and SQNR calculation. We will test different bit of resolutions 2, 3, 4, 6. Bits test 2, 3, 4, 8, 6, 4, 6, 8. Here's the result 2. First, we will know the basic concept of quantization. What is called quantization? A continuous amplitude signal can have an infinite number of amplitude values. However, in a digital system, we need to represent these values using a finite number of levels. This process of converting the amplitude can into one of these finite levels called quantization. For in bit quantization, the total number of quantization level is 2 to the power n. For example, here we can see 4, 2 to the power 4 equals to 16, 2 to the power 6 equals to 64. The process is converting the amplitude into one these finite levels called quantization. These finite levels, or you can see this in orange lines. Then in PCM encoding, what is called PCM encoding? After quantization, every sample has a corresponding integer index. The index is converted into binary number. For example, if we use 4-bit PCM and the quantization index is 5, the binary representation is 0101. Therefore, each quantized sample is represented by n-bit PCM word. In our program, we also perform a validation check, make sure that every PCM word is exactly the required number of bits. So for a 4-bit system, every code word must contain exactly 4 bits. Original and quantized waveform. The first visualization, we will see the original and quantized visualization of 4-bit. The smooth curve represents the original sinusoidal signal, while the staircase-like signal is quantized version. For a low number of bits, such as 2 bits, the quantized signal has only 4 possible levels. So the approximation is quite coarse. When we increase the number of bits, the number of level increases. As a result, staircase becomes the finite and quantized signal follows the original sinusoid much more closely. So the physical effect we expect is more bits, more levels, smaller steps, smaller quantization error. Here quantization error, you can see this. Uh, this error calculated as En equals to xn minus xqn, where xn is original signal and xqn is quantized signal. For an ideal uniform quantizer, the error should approximately remain within minus delta by 2 to delta by 2. Here delta means quantization ratio. As we increase the number of bits, delta becomes smaller. This is the delta. Yes, therefore, the range of the quantization error also becomes smaller. The histogram gives another way to observe the distribution of this error. Minus 0.6 to 0.4, you can see and compare this with this histogram. Now, we will see the ABC and SQNR. We calculate the mean squared error or MSE. MSE measures the average part of the quantization error. It's called as the average of the squared values. Next, we calculate SQNR, which is uh, formula is 10 log 10 P signal by P signal by P error. A higher SQNR means better signal quality and less quantization errors. For ideal full-scale sinusoid, the theoretical SQNR is approximately SQNR formula is 6.02 and plus 1.676 decibel, or somehow you can some books say 1.6.6 n plus 1.8 dB decibel. This means every additional bit should improve SQNR approximately 6.02 decibel. You can see this in this result table where two bits at level 4 MEC 0.02, and the theory measures SQNR, and theory of SQNR um, shows me very coarse quantization and large error, very coarse quantization. And in the second bits, 3 bits 3 and labels 8 to the power 3 equals to 8, you can see better approximation. Here you can see the better approximation in uh, in bits 4. You can see noticeable smoother waveform. Here you can see much smoother, means closer, and small in bit 6 smaller quantization error, and bit 8 you can see uh, quantized waveform closely follows original. Every additional bit increases SQNR by approximately 6.02 decibel. Thanks, sir.